Right, so now we're going to try and prove this polar decomposition that we talked about in the last clip. So namely, given any operator on V, we can find an isometry S such that our operator looks like the isometry times this positive operator here, which we can think of as being the magnitude of T, or playing the role of the magnitude of T. All right, so this is going to be broken into 3 parts. Hence the title here, part 1. And in order to, so when you look at something like this, you say, okay, so how would we go about proving such a thing? We're actually going to construct what the operator S is. And you see that we apply first this operator, root T star T, and then this operator S. And so what we need to do is we need to take something that's in the range of this operator and apply S and get something that's in the range of this operator. So that actually shows us that the way to begin is to look for a way to define an operator from the range of this to the range of that. And that's where we start. So we are going to define an operator S1 from the range of T star T to the range of T. And we're going to do it by saying, let's see, S1 of, and now something that's in the range of T star T root looks like this one. Right, so that's something this guy right here is a generic thing from the range of the square root. Okay, and so what we're going to do is we're going to define this to be TV. Okay, so that's fair enough. Now, does it make sense? Well, we've got to check. So to see that S1 is well defined, we have to consider the case that we've got 2 different things. So now if the square root of T star T were injective, we wouldn't have to worry about this. We could take the unique thing in the preimage and then apply T to that, and we'd know everything was good. But here's the thing, this is supposed to work for any old operator. There's no requirement that it's injective, right? So what if when we apply this thing to V1 and V2, we get the same thing? Well, then according to this definition right here, we need to have it be the case that TV1 equals TV2 or we're sunk, right? Okay, so that's what I mean by checking that it's well defined. So let's see. So if we look at the difference between TV1 and TV2, then this is going to be the magnitude of TV1 minus V2 by linearity. And this is equal to the inner product of TV1 minus V2 TV1 minus V2, and then we can move it over using the adjoint property. And then we know that T star T is positive, so it has a unique positive square root. So we use the defining property of the square root. And then we can move this one back to the other side because as a positive operator, it is self-adjoint. And so that gets us the magnitude of T star T in the root applied to V1 minus v2, and then finally expanding this, we get 0. So that shows us then that TV1 has to be equal to TV2. Okay. But we're not done. This shows that S is well defined, but so far we just know that it's a well-defined mapping from the range of one guy to the range of the other guy. We still need to check that this is an isometry. Okay, so let's see. So then this is an isometry because if we look at the magnitude of what we get when we're done, maybe give myself a little more space there, this is going to be, let's see, and so we're back to inner products. So this is the inner product of TV against TV. And so then we've got T star TVV, and we can split again. And so this is basically the same kind of calculation that we just did. And then so we get the same norm. Okay, so that shows us that it's an isometry. And now, since S1 is an isometry, it's injective. So its null space has dimension 0, and then that tells us that the dimension of the thing that we started with, which was the range of this guy, that's the vector space we started on, is equal to 0 plus the dimension of the range of T by the rank nullity theorem. Okay, so they have the same dimension. All right.